PowerPoint labs, PowerPoint labs, then
if I can find the full screen properly.
Oh,
Right.
slide.
I don't want anyone in my group except me.
Oh, but that's thank you. Okay.
Hey, Matthew. You make sense.
Okay, I think I'll begin first. Hopefully no one goes through the front door while I start. And I'm going to be stuck here even though I actually want to stand there because I actually need to push the button.
Wireless mouse.
Your wireless mouse.
It's okay. I'll set that up next week. Okay, I think I know most of you. Actually, there are quite a few new faces, but welcome anyway. We have our own DYOM for data structures. I think like for most of you guys, you should like if you've taken like 2040S or 3230, mostly most of the time for data structures for us, we do inserts, deletes, lookups, and maybe like rank, select, predecessor, and so on and so forth. Basically, we'll be covering some of that and like beyond basically. So first motivation, why do we study data structures? Besides the usual stuff that we talk about in terms of like maybe from CS 2040 and like 3230, I have to mention a few things. First of all, what I hope to do for this class is that I'll give you more tools for problem solving. So maybe in terms of like interviews for internships or whatever, the whole idea here is that I really want to emphasize that basically what you learn here hopefully will give you like more different ways to sort of like solve either the same problems or newer problems, and you won't be constrained by the same things that you just learned in your usual syllabus. Okay, so like for example, shortest path, MSD finding, nearest neighbor searching, these kind of things, we're gonna like touch them up again, or like basically maybe even cover new things. Okay, we've all been like sort of like I mentioned been taught standard data structures, like BSTs, ABLs, heaps for example, so on and so forth, right? But I also want to like raise an important question, which is, are these optimal? Have you been really taught the best solutions to solve these problems, or have you been taught like fast solutions? But not really like the fastest, like where do we stand on this? You've been taught that these like some of the solutions that you've seen in the previous classes are good, right? But are they really like the fastest you can go? I'm gonna touch on some of that like during this course, and I would really like it if you keep asking these questions to yourself. Like the things that you've been taught, are they like really the best? Can we always improve on it, right? So can we really do better? This is like an important question. Like always in CS, you ask yourselves, can we always do it faster? Can we always do it better, right? And the last point that I want to point out here is that I hope you're all here because it's fun. It's really fun to learn new things. It's really fun to touch a new topic, right? And I find these ideas cool. So I promise you, like at least from my perspective, like what we're gonna see is really cool and interesting ideas. They're really new, okay? And I hope like at some point in time you're gonna be like, wow, I never thought of doing things like this before, like how you would in 3230 2040S, right? And this is actually one of my favorite quotes. It's from a computer game, which is like the guy actually literally says, just remember, efficiency is clever laziness, right? So sorry. And I really want here, like want all of us here to learn to be lazy, but like in a clever way and not in like a really lazy way. Okay, so to reiterate, these are some of the questions that like I would like us to like pose to ourselves, right? Are there assumptions about the data that we can use to like speed things up, right? Can we like take amortization and randomization into account? For those of you who haven't taken 3230, like don't worry, I'll be covering these concepts. So like for the rest of you, it might not be new. I'll basically just cover like the hope is that we'll cover just enough so that you can actually handle these topics. So this will be like as beginner friendly as possible. The last question is, are there ways to make these data structures practical? Like there's a lot of concern about how these things are theoretically interesting, and a lot of them, like some of them you're going to see, actually even though are good in theory, aren't actually really good in practice. The reason why is because they have high constant factor like costs, or maybe it's because it's just too difficult to implement, and in the industry we really don't have to go that far. And you're going to see some where they're actually so good that they're preferred over most of the stuff that you've learned in 2040 or 2040S or 3230. So we're going to see a mix of both, right? But we'll talk about that, and we'll talk about why some of these are made special to like in the hearts of like people who are like practically minded versus the ones who are like theoretically inclined. Okay, so in this course, let me just do a quick summary. These are the things that we're going to cover. I've sort of like broadly divided them into 3 categories. The bit trace and divide and conquer section, basically we'll talk about how if we had, for example, more knowledge about the data, like if we knew that it came in bits and we could represent it in bits, right? Or if we could try to apply divide and conquer not just to algorithmic problem solving, but to data structures as well, what do we get, right? I've listed some of them there. This is what we'll hopefully be covering. Actually, we definitely will be. I insist that we cover it. The next one is randomization, which plays a big role in theoretical CS as well as hopefully practical like implementations. You're going to see some stuff that you've seen there before. Linear probing, for example, isn't new, but I'm going to actually show you that it actually practically is very useful, even if like you've been told it's not. And then again, I want to reiterate randomization, like one of my favorite ideas. We're going to see used not like in data structures. If you like to see in randomized like in algorithms instead, like I highly encourage that sometime in your undergrad career you take CS 530 as well. They'll cover randomized algorithms. Over here, we'll cover like randomized data structures. And the last portion that I want to cover is like handling non-standard operations and factors. So like you've seen, like I said, rank, select, delete, insert, lookup, and so on and so forth. But you know, what if you wanted to do like, what if you wanted to be cache efficient, right? What if you wanted to handle strings? Those kind of ideas. These things we probably haven't touched a lot about in your standard courses, and I want to kind of like expose you guys to those kind of ideas here. Because you know, like I don't think we'll get a chance to anywhere else. So moving on, let me just quickly like cover like some of the standard stuff that people do like in their courses. In this course, I'm going like there's basically two things I'm going to emphasize on. Like one portion is analysis of your data structures, like your space efficiency, you know, your time efficiency, and so on and so forth, as well as taking into account randomization and amortization. And the other portion is design. So basically, I'm going to really try to do my best to walk you through the design of these data structures, and hopefully you'll see the motivation into like, you know, like, okay, what were they thinking when they were designing these data structures? You know, what was their mindset, and like what was their key goal, and the kind of steps that they did. And hopefully, like, you know, if you get these techniques, you could probably try to apply them whenever you have to in the future. Okay, so by the end of this course, what I expect you guys to be able to do is sort of like, in the context of like data structures, like probably try to randomize things, like understand how to randomize things, or maybe try to amortize it. Okay, and like maybe take into account external memory costs. External memory costs is probably not something you've heard of right now. I'll introduce it when we come down to it, but like it sort of makes you a lot of money, like, you know, because like people actually really use that in real life. Besides that, you know, I kind of want you to be able to use these data structures, not just make them, but of course they have to be used. There's no point designing a data structure if you're not going to use it for algorithmic problem solving, right? So I'm going in like the assignments, I'm going to like, you know, try to bear in mind that I'll set you a question where you really need to make use of these data structures. There's no point making a data structure if you're not going to use it. Okay, so like for the deliverables, I know we've talked about this. Let me just quickly mention again so we're all on the same page. There's going to be 10 assignments, around 3 to 4 questions each. Okay, the way that I'm going to try to set it is that there'll be two easy questions and 1 to 2 challenge questions. The 2 easy questions are going to be set in the mind that if you paid attention to the lectures and you understood the content, you'll be able to answer them, no problem. And it should take you like, it should be of no difficulty. The last challenge question is pretty much just, you know, in case you guys really want to solve a puzzle at the end of the day. You know, it's like a brain teaser. Don't expect that one to be easy, and I hope that, you know, we all understand it's all in good fun. I'll set it so that the assignments are due 1 week after each release, and then give us some me and the teaching team some time to grade it, and we'll get back to you with feedback if we can. Also, at the end of the semester, I would like you guys to do presentations in 2-man teams. I know like presentations probably, like you guys might not be a fan of presentations, but the reason why I want you guys to do this is because I think it's a really good way to test and see whether you guys, at the end of the day, can be independent. And at the end of the day, whether, you know, after we've like parted some of our techniques of like, you know, analysis or like understanding data structures, for example, whether you can actually go out and do that by yourself and on your own. So don't worry too much about it for now, but basically I'll talk more about it later on as the course progresses. Okay, so that's the weightage shown on the slides. Don't worry, I've already uploaded them to Piazza, which is the other thing. If you haven't joined Piazza, please do, because I'll be uploading all this stuff there, right? This is already uploaded, so whenever you need to reference it, it's online. Okay, I'm going to say that I'll set the passing rate at 55%, but I really don't want you guys to worry about the grades, because this is, you know, it's supposed to be like chill, but at the same time, you guys need to get like some minimum amount of work done, right? As long as we're all clear on that, I think we'll all be great. Okay. Okay, so for the assignments, like I mentioned, you know, this is just here in case like you guys like don't remember and like download the slides and like re-clarify. The point is, again, you know, if you try to do well, just try to understand. We all know each other here. There's no pressure. There's no grade. So please don't try to like cheat or anything. Okay, like, you know, just do your best to try to understand the question, answer the questions. For the presentation, like suggested topics, it's fine if you guys don't know much on your own for now. Okay, so I've actually like prepared like a lot of topics for you guys to choose from. Okay, you don't have to pick them right now. Halfway through the course, for example, maybe you'll see something like, you know, related to hashing or something related to web trees, and you get very interested in it. You know, you go like, wow, you know, like I want to learn more about this. Some of the stuff that I'm presenting, right, their extensions are actually on this slide, and some of them are actually very new. Okay, and my hope is that you guys actually get to pick some of these topics and present them. I actually really wanted to cover these topics, but I thought it'd be pretty good to actually let you guys have a chance to present them as well, so that at the end of the day, at the end of the course still, we all still get to learn something. Alright? Okay, so let's see, what's next? Okay, yeah, wrapping up. So basically, the course coordinators would be me, Alden, Zhijian, and Irham, and we have Professor Honwai with us. Okay, and these are our emails. So if you have any questions, please email us. Feel free to email us. You can text the three of us on Telegram as well, or you can have discussions on Piazza. And I really hope that that's what we do. Okay. So with that in mind, there's like nothing else. So I'm pretty sure my time is over. This week we're gonna cover binomial heaps and Fibonacci heaps, which is done by Prof. Online. Okay. So with that in mind, I'm gonna hand over the time to him. Great. Okay.
You want to go, right?
Yeah. No. I'm just gonna record audio. Just
Oh,
in case.
that's recording.
Yeah. So like.
Audio.
Yeah, because like the row is like.
Will it
recording.
be loud enough?
Yeah.
Okay. Let's switch this thing back. Okay, before I start, let me just find out, okay, so you know most of the people here, I don't, okay, so how many of you are in year 4, that means final year, okay, quite a number, okay, how many in year 3, okay, year 3, year 2, okay, anyone in year 1,
Me.
okay, okay, so you're in here because you took all the other courses already, is it? Okay. Okay, Ken, my other question is, I assume you have heard my lecture before, some of you, at least those who are in year 2 and year 3, okay?
GQ.
Because of GQ, right? And I think I'm glad to hear Alden say one thing. I think you come to university in order to learn a skill set, right? And I think there will never be another period in your life of 4 years where your learning is so intensive. Okay, sure, after that you can, of course, do some other stuff and so on, but never, okay, all right? Even a PhD is not as intensive as a bachelor degree. Okay, people think that PhD is very tough. You really sit down and talk to a PhD student, and you track how much time he actually spent on work, okay, versus doing all the other kind of stuff and so on, okay, it's never as intensive as an undergrad, okay. So, so during this period, what do? Okay, of course, you take all the courses, you do stuff, but actually, what is more important is the attitude, okay, you develop, okay, a mindset. I think in my cue, I allude to some kind of a mindset, okay, stuff. But I think since you're in this class, I think the mindset is given homework, what do you do? Okay, you can, you know, I believe today, if you search hard enough, Google will help you find the answer. Okay, all right, but that's not the point. That's not the point. The point is that, you know, Google help you solve the problem. So what? Google became smarter. You did not become smarter, all right? So actually, the challenge is for you to get the thing yourself. And also, there's no joy. You know, if you work on the problem, it's really hard. If one of the challenges that he's going to give you is going to make you stay up all night and, you know, try to solve it. Okay, when you finally crack it, you feel the joy. And also, you will remember it for life. Okay, so in fact, some of the things that you mentioned, I'll mention them later on today. Okay, but I told Eldon, as you are preparing your slides, his slides, and also later on when you are doing your project, okay, it's very important in every piece of research work to do the 5 Ws. Actually, I call that the 6 Ws. You know what those Ws are, right? What are those?
Who, what, when, where?
Who, what, when, where, why. One more?
Who?
How? Okay, okay? I write how like that, okay? So the 6 W, okay? Because 5 W and 1 H is a really crazy thing, so I just twisted this, okay? But actually that's the point, okay? Nobody, you know, okay, there's no rule that says I cannot do this, okay, all right? If it helps me to remember things and so on. Now the reason I think this is important, and today I'll bring you to that point, is this, okay? Progress in science, progress in computer science in particular, but when I do Q, we talk about progress in science, progress in philosophy, economics, and so on. there is always the 6W that people talk about. Okay. In computer science, in my research career, okay, actually there's one slide that I don't know whether it is here or not. It's not there because I didn't bring the slide. Okay. I've seen research problem become important and then disappear, no longer important. Okay. For example, the Bruin graph, one of the topics that you mentioned there, was invented a long time ago. Okay? And people studied it. Then they said, we don't need it. Okay? And it resurfaced again about 10 years ago. Okay? The thing came back because we now do computational biology. Okay? And we went to sequence the DNA. Okay? The Bruin graph methods turned out to be much better than the other methods based on TSP. Okay? So, in my own career, you studied 2100, where you do all this logic gate design, and the key was how do we minimize the number of gates, right? If you want to build a circuit, because the number of gates will then have a major impact on the size of your chip, and how much power is going to burn, and how fast or how slow your circuit is going to go. And so when I was a graduate student, there was a professor who said that, he had a research result, okay, that minimizes the number of gates. He has a method, but when he sent it out for publication, it got rejected because he said, now we don't care about the big gate count anymore because we have integrated circuit. We can pump in tons of logic gate into one IC. So not that the problem, okay, is not solvable or was solved, but the industry didn't need it anymore. Okay, and many years later, he said that 20 years later, I submitted the same paper. I only need to rewrite the application, and it got in. The reason was that the IC chip also becomes saturated, and today, even though the IC chip now contains millions of gates in one IC, it is saturated already. That thing is so dense. Okay, that's why we need a lot of power to cool down the circuit because it is very dense. You never want to touch the CPU, for example, in a server. Okay, it will burn your finger. Right? Okay, so the problem goes and it comes back. Okay, so the same thing. Okay, it's very, very important. A piece of research may be important because at this time, sometimes there are research results that were invented but never got implemented because we don't have enough memory, we don't have this, and we don't have that. So when the time comes when we have all this technology, we can then implement them and they can run very well. Okay, so when and why and all that thing are important. Okay, so this is my. I have not touched a Windows PC for an extremely long time, and this is a very funny keyboard because it has a huge number tag. So every time I press this, I end up pressing the plus sign and all that. So, sorry about that. Okay, yeah. I came here very early. I think some of you saw me, and I was veteran. I can't give up. Okay, I'm going to just use it. Okay. So today we're going to see a bunch of things. I'm going to run through this very fast because these are fairly elementary. I want to get you one important thing. Okay? Why did the researcher want to study this problem? And number two, what are the key ideas that bring them there? And if you don't get all the technical detail, it is not that important. The most important thing is to get the main idea. The reason is the technical stuff, you can always, dig it out, and you can take your time to do it. But the important ideas are the ones that you want to keep. Okay, so I will try to run you through that. Okay, so, and the story I always have THM. Okay, THM doesn't mean theorem. Okay, it's a take-home message. Okay. Right, THM is take-home message. Okay, I've always liked this topic because it's a story of elegance and speed. Okay, and you achieve speed via some smart analysis and also smart laziness. Okay, as he also said just now, it was about clever laziness. Okay, things like that. Okay, so if at the end of this lecture you get that, okay, I think that's the good take-home message. Okay, so let's take a look. Okay, and I'll first take you through the time. First of all, in the 1950s, nobody cared about data structure. Computers were just being built. Okay, so nobody cared, and memory was very, very, very expensive. Okay, they were done by core memory. Okay, there's a magnetic core, which is a round little thing, can be oriented this direction or that direction. Core memory, we call that. Eventually, core memory, the name stick, although it means something else now. Okay, but during that time, nobody studied. So if you read many of the old papers, okay, Dijkstra's algorithm, for example, he never mentioned any data structure. Okay, the reason was that at that time nobody cared about data structure. Okay, so data structure came along the study long time ago. I think those of you who remember Lee Hsien Loong wrote a computer program to solve Sudoku. Okay, and when he was interviewed and he was talking about this, he remembered, because a long time ago we were trying to save a lot of memory. Okay, you talk about bit. Okay, we were trying to store two numbers in one word. If your number maximum size doesn't exceed so many bits, I'm going to compress that into so that it is hell for somebody who don't know what you are doing to try to decode your program. Because every word, every time you want to do operation, you have to go and strip out and get back the word out first. Okay? So an addition operation become very complicated. So that was the kind of thing that they were doing at that point. Okay? So in the 70s was the good time. And you go back, you see a lot of advances in data structures in the 70s. Okay? I do want to give you one motivation first before I start. Okay? So who is the one who is the oldest here then? So those of you who are, okay, anyone who is 24 this year? This year, that means going to be 24 this year. Okay. Anyone going to be 25? I don't expect a number, a hand going up. Anyone going to be 25? Okay, one. Okay. Okay, two. Okay. All right. Now for the rest of you, okay. You know there is a famous Turing Award winner who wrote a very important paper when he was very young. Anyone want to make a guess? Who was that person? Since you're in this class, I assume that you like doing stuff. Okay, so I want to give you a motivation to do. Okay, okay. You have presumably heard of quicksort. Okay, quicksort. So who invented quicksort? Okay, Tony Hall. Okay, yeah. Okay, his actual name is Anthony, but all his friends call him Tony. Okay. So Tony Hall invented quicksort, and he did an analysis of it. Okay, wrote a paper. It's a very short paper. Okay, 3 or 4 pages long. Okay. At that time, he was only 26 years old. So all of you are reading his paper, his invention. Okay, quicksort algorithm. Okay. Not everyone look at the analysis, for example. Okay, quicksort actually has a very beautiful analysis. Okay, all right. And he was only 26, so you still have time. Okay? Some of you have only 1 more year left, but never mind. Okay, all right. Okay, okay, all right. Okay. You still have time. Okay, all right. Okay. Okay, so let's start. What is priority queue? So I'm going to go very fast here. All of you have already studied ADTs already. Okay, so okay, and we do ADT because so it's a priority queue, meaning that, instead it's always there. Priority means that, and we're going to assume that whenever we talk about priority, we are talking about minimum. Okay, you can always revert it and do maximum, but we're going to assume that we are doing minimum. So finding what is the minimum and then removing that minimum is important. Okay, if you have these 3 things, you have the essence of heap sort, right? For example. Okay, and actually, one of the first data structure was a heap, and the heap was invented. While the person was doing heap sort. At that time, he was of course using a max heap, but you can turn it around and do it for min heap. Okay, later on, it became important to have a new operation called decrease key. right? Okay, I assume again you have seen something like that before. Okay, decrease key. It just takes an element x, okay, and reduce the value, the key value of x by k, okay, or actually no, replace it by a new value, okay, which is smaller, okay, all right. It being very small, smaller is important, okay, in this particular context, okay. But often there are also other operations that are important, okay. Delete sometimes also important, okay, melding, and all of this we want it to be fast, okay. The whole point of doing a heap is we don't want any of these things to be order n. Increasingly today with modern languages and allowing you, okay, the access to libraries that have already been pre-programmed, there's the danger that your program can run very, very long without you knowing it and without you knowing why. And the reason is that the API is so convenient, you call it and it was an order n operation and your n is very large, okay, all right, so at least I don't know whether Stephen Halim still does it, but whenever I teach 3230, I'll make sure that there will be one data set that will kill everyone, okay, with time limit exceeded if you don't use a log n operation somewhere, okay. So we are always talking about fast operations, okay, all right. So let's look at the history and the timeline, okay, all right. As I said, okay, the only exception is binary heap because it was invented for sorting actually, okay, by Williams, okay. But okay, so bring you back in the early 70s, okay. Pointer data structure, you know, of course now students struggle with pointers, but pointer structures were not that important. If you look at Fortran and all these early languages, okay, they don't use dynamic data structures, okay, all right. But eventually, okay, once we have dynamic data structure, leftist heap was the first one that allows you to merge two heaps together, okay. Merging two binary heap is a killer, okay. It's a no-go, okay. And we'll tell you the motivation why it was binomial heap invented and why Fibonacci. And after that, then came a slew of data structure. Okay. Robert Tarjan came in at the right time. He was a graduate student. Okay, he was a PhD student at Stanford who happened to have, okay, Professor Bob Tarjan, John Hopcroft come to visit for sabbatical at Stanford. Okay, and so they started doing some work that led to the Turing Award. But okay, and so Robert Tarjan did a lot of data structure work. Okay, after he got his own PhD, he supervised a number of students who worked on a lot of data structure stuff. So if you look down the road, there's a long list. Okay, I wrote this set of notes a long time ago. Okay, didn't push off the rest of the heap-related data structures there. Okay, I want to give you the running time. So binary heap, we can do all of these things. But we cannot meld. We cannot join two things together. Okay, all right. Leftist heap solve this problem. Okay, it's able to merge two heaps, but delete and decrease key cause them problems. Okay, so there's no time bound. So anything that's missing, there's no logarithmic time bound. Okay, and so binomial heap. If you look at this time, then the motivation is I want to have a heap that can have everything in order log n. Okay, and turns out, okay, this French, okay, computer scientists solved this problem, okay, all right, and I'll show you the motivation for the next one, okay, all right. So why do we care? Okay, we care because of this, okay. At that time, actually both of them wrote the two algorithms, okay, one for single source shortest path and the other one for binary spanning tree, and they were saying that, okay, this is at most n squared. So if you really look at Dijkstra's algorithm, okay, his paper, original paper, he only talked about this thing being okay, n squared because it can be done, okay, in n squared. Okay. But of course, we then look at the same algorithm and we say with some data structure, we can make them more efficient. So if you think about it, okay, his algorithm uses, okay, extract minimum, choose the shortest edge of some kind, okay, sometimes the shortest label, and the other one is decrease key, okay. I'm assuming you know this. Is that a reasonable assumption? Okay, I have some slides in case you don't, but I'm going to skip them. I plan to skip them. So with that, and okay, so here's the queue that you're going to implement using the data structure. If you use a straight array, which was original Dijkstra implementation, then this thing is going to kill you. Okay, all right, you will get order v squared, and this is fast. Okay, this is very fast because I have a key and I just decrease the key. It's a constant time operation. Okay, all right. So, but it's going to be v squared. So if you use any kind of a binary heap or any kind of heap, okay, you get this. Both of them will be log v. Okay, and so in this case, the running time, okay, the larger one, this is v log v because I do this v times. This is e times log v. So okay, the dominant term comes here. So we have moved most of the work from here over to here. Okay, so data structure is really, the study of data structure is really about that. We want to know what operations you need. Define the ADT, and then say, how can I structure my data so that I can do this faster or that faster? Okay, all right. So this is the way things were at that time. Okay, and so I'm going to skip all this other stuff. Okay, that talks about this thing. Okay, so. The key is really to do Fibonacci heap. Our target is here. Okay? But to get here, it is elegant to talk about first binomial heap and then move from binomial heap to Fibonacci. Okay? In 2 steps rather than 1. Okay? So if we have this, then the time bound is order 1. Actually, I should put a little asterisk because this is order 1 amortized time. Okay? Most of these are amortized time. Okay? Not worst case time. Okay? All right, but using that, we can get this, okay? All right, so I'll show you this later on. And to move to the end, to talk about what, okay, Alden had said earlier. So, okay, so this was John, Willman, and he proposed this. This is a very elegant data structure. This is one of the nice things about it, okay? And Tartan wanted a specific thing in mind. He wanted the decrease key to be very, very cheap. Okay? And so with that, we got Fibonacci heap. Okay, all right. And so these 2 people, I don't know whether you know them or not. Okay, Stefan Naher and Kurt Melhorn. Okay, at Max Planck Institute in Germany. Okay, and they programmed it in Ladder. Anyone of you heard of Ladder? Used Ladder before? It's a library of very efficient data structures written in C++. Okay. All right, and Fibonacci heap is there, okay, as one of the, okay. So you don't need to program it up, okay, it's already programmed if you have later, okay. There was a time when I taught my advanced course and we used later for some of the programs, okay, we bought a copy of later, okay. So let me quickly go to binomial heap. Okay. So many data structure does this, but no one can have all of this. So this was the first one that basically solved all the operations in log n time. So we have all these things back around this time. Okay, can we do all the operations in log n? As it turns out, okay, it is a very simple, very elegant structure. Okay, and it is defined like this. Actually, this one slide tells you everything about binomial heap, or almost everything. Okay, all right. Recursive definition, we have binomial tree, okay? B0 is 1 node, okay? B1, for BK, we take 2 copies of BK minus 1, and because we have a min heap, we compare the root, okay? And the root, of course the root is the minimum, right? Okay, so whichever one is smaller, those become the new root, right? Okay, and so we do that. So here's an example, B0. I'm only going to show you the structure, not the value, because the value we always assume that heap property, okay, will prevail. Okay, so this is B1. To get B2, I take 2 copies of B1, take the smaller one, turn that to a root, and we get this structure, right? Okay. But notice that if I move on, okay, each one of them is 1 additional operation only. To produce this, I take 2 copies of this, 1 additional operation, I do that. So in order to calculate how many operations are needed to construct this B3, we know count the edges. Did you see that? We just count all the edges, and that will tell me how many operations, how many comparisons were needed. to build this thing. Okay? So I often tell students, how do you know you have perfected and you really understand something? Okay, people can look at this same picture, and it depends how much information you can extract from the picture. Okay, I often think that education is like teaching you a new pair of lens. I put this on, and suddenly you see more stuff than all the other people. Okay, right? So by looking and making sure that this is the one link, because this is the only link that is new, right? So to produce this thing, I took what was done previously, I do one additional operation. So the link are order comparison that I needed to build the structure. Okay, all right, and the year before. Okay, and given this, it has another very beautiful property. Okay, and this beautiful property is that a PK consists, this is one way of looking at it, this is another way of looking at it, two different views of the same structure. Okay, see? It has one copy of B0, one copy of B1, 2, 3, 4 until K minus 1. Okay, now this structure, this property is useful later on when we do analysis, okay, of some of the operations. Okay, so now we can prove some properties. Okay, so if I have a binomial tree of order K is the order, okay, then there are 2 to the K nodes. You can prove that by induction. The height of the tree is K. Right? The root has degree K, and deleting the root will give us binomial trees of size 0, 1, 2 until K minus 1. All of these can be proven by induction, so I'll leave it to you. Okay? All right. So now we're going to look at this tree. Okay? All right? And why is it called binomial? Because of that property. You see? It gives you basically the binomial expansion, right? Can you see that? Okay? Right? You look down at this one, this is 1, 2, 2, 1, right? And down here, okay, sorry, yeah. Correct, 1, 2, 2, 1, and then here is 1, 2, 1, and so on, and you take the next level, it will be 1, 4, 6, 4, 1, right? And so on, okay? So that's why the name binomial, okay? All right. So, but that gives me only trees of size 2 to the K of on some K. So if I need a heap of size 13, what do I do? Well, here back, okay? I'm going to, if I are 11, for example, what I do, I'm just going to take one of size 8, one of size 2, and one of size 1. It is really like binary representation of the number 11, isn't it? Okay, so, okay. All right. So everything about binomial can be thought of as how to take a number 11 and break it down into binary. Okay. Since we are talking about binary, okay, people ask me how long I taught here, and I said, you know, I've taught here for 100,000 years in binary. Okay, okay, you can figure out that out. Okay, all right. So here is the right. So the numbers are here. The numbers are stored here. If we assume the heap property is satisfied, and this is satisfied trivially, if we just do that operation, we call that the linking stack. Okay, and we have this. The question then is this, okay, some of these binomial things have a large number of pointers. Okay, so in that case, when we have order K and we need to store, that would not be efficient, right? So we need, okay, of course there's one way, a standard way to take something like this and turn it into a binary tree. I assume that you have heard, okay, you have studied that before. Okay, but in this particular case, it's a nice structure. Okay, all right, there are at most, okay, log n plus 1 binomial tree. Okay, there's a limited number, there's a log n number of them. Okay, right, so, and as I said, 11 correspond to this in binary, so you will see there's one binomial tree of that order, one of this order, one of this, and none of that order. Okay, right, so now we are ready. So first of all, how do you represent this? Okay, so to represent this, I'm going to define this structure. Okay, you need 3 pointers. Okay, to make it efficient, okay, one to point to the parent, one to point to one child, only one child, okay, and then one to the sibling. The sibling will link up all those at the same level. Okay. We need a key. Okay, this is the important one, and the degree, parent, child. These are 3 pointers. So 3 pointers and 2 values. Okay, and this tree looks like this. See? So it points down to one of the child, and that is good enough because there is a linear linked list, okay, that points to all the children, okay, and every one of them have a pointer to the parent node, okay, and this will help us to define that binomial data structure, okay, all right. So every node, can you see now, apart from the degree, okay, the degree, the rank, okay, right, we'll have these 3 pointers, okay, this is from the book, okay. So now we're going to ignore how you play around with the pointer, and we're going to just use this representation, just like we do for a heap. Okay. Right. So first, how to make a heap? Well, very simple. It's just nil, nothing. Okay. By the way, we do not know which one is the smallest. To know the minimum, we need to search. Okay. Right. So for minimum, we need to search. Yeah. Okay. Scan the root list, right? Okay. Don't need to go down below. Okay. So we scan the root list. Okay. Now the next thing is how do we link things up? Okay, how do we do this linking step? Okay, this particular linking step that takes the 2 copies and then links. By the way, we only merge if they are of the same rank. Okay. So we take 2 of the same rank, okay, Y and Z. Okay, and if we assume that Z is always smaller, then Z becomes the new root, and we have this, and here's the code to do this. It's order 1, right? Clearly. Okay. Actually, if you think about it, although we write it down like this, when we show this diagram, we have to think about the pointer structure flying all over, right? So what do we need to do? We first point the father of this guy to be him, right? Can you see that? That's that. Okay. Now after that, we need to link Y to the child, because now this node is at the same level as the next level over here. So we point the sibling of Y to be the child object, the first child. Remember, the first child is here, so we need to link these 2 across. Can you see that? Okay, so that's what this does. Okay, then child of Z, okay, and then the degree of Z to be increased by 1. Okay, the degree of Y does not change. Okay, so here's an example to show that, convince you that they can all be done in constant time. I'm not going to do the detailed code for each one of them, but this is enough so that you know that all the pointers can be resolved. Okay, this is an example of the details I said I will skip. You can always look at the notes. Okay, confirm. So that is to link only one binomial tree and another binomial tree. That if I give you a heap of size n, a heap of size m, how do we combine them together, right? Okay, and so this is what you do. Okay, so suppose I have this 3 binomial heap, okay, and this binomial heap of different sizes, then the beauty of this thing is it is actually the same thing as binary addition. Okay, what do I mean by that? Well, 19 is represented like this, 7 is represented like this, and they can be stored using those 3. And when you do a link union, you will get a final answer of length 26, of size 26, and it will have all this. And so that's what we actually do. So for binomial trees, union is almost like binary addition. Okay, so here's what we do. Okay, I take these 2, I do a linking step, right? B0, B0, give you B1, right? Now I got 3 copies of them, so I again link 2 of them together. This one and this one, I link them together, right? Okay, and this one, I bring it down. Right, becomes the output, right? Output. This one not ready to go output yet because I will check, right? This one. Okay. So isn't it addition with carry, right? So we do the same thing. It has 1, and I check, there's nothing at the bottom, so I bring this guy down, right? And the next one, I bring it down. So it is just binary addition. All you need to do, define a link step, and after that, it's just binary addition. Okay, and it's very clear, it's log n, right? Okay, so here's what we do. Okay, so that's what we did. Okay, given a heap of size, okay, n1 and n2, left n1 plus n2. In fact, okay, right, this will still be order log n because the total sum can only increase by n-1. Okay, all right, and these two addition, so the running time is order log n. Okay, very clear. Okay, so now once I can do that, how about insert? Actually, insert I can do it two ways. One is I can think of the new one as a new heap, right, of size 1, and union them. Okay, finish. Okay, so done. Okay, so that's the easy way. Okay, so one powerful thing that you learn, hopefully from this thing. Notice I like this treatment because we define one basic operation that allows me to bootstrap myself to define a union operation. Union operation then allow me to do insert very, very quickly. You will see that it will also be used to do other stuff equally easily. Okay, right. So extract minimum. Now we have a problem because extract minimum is going to destroy part of the property of that thing, right? Okay, so far we never, right? Because when we union them, the property always preserved. Correct? So now we have a problem because you take, well, the minimum must be one of these guys. In particular, this one is the minimum. So when you remove it, but we have the previous property, remember? Once you remove the root, I break it out into a bunch of stuff, right? And this bunch of stuff is just not independent. There is also a link, a linear link that links them, right? So I can treat this whole thing as a new binomial heap of size 2 to the k minus 1 and union them together. Can you see? And so that's what you do. Find the minimum, remove the root, and by that property, okay, I can union them, and so union also gives us this. So, now how about decrease key? Okay, and delete. What about decrease key? Okay, suppose here's the problem, 17, I decrease its key to 5. What can we do? Well, the other stuff don't change, right? I just need to make sure this one is smaller than this. I swap them around, right? This is like shifting up in the binary heap, isn't it? It will keep going up. Okay, the structure don't change, only the elements get moved around. Does that make sense? And the height of the tree we proved to be log n already, right? So there we have it. So all of these things can be done easily. Okay, all the things can be done easily. How about deleting one of these funny guys here? Suppose I want to delete this guy. Suggestion.
Bubble up, then delete it.
Okay. Say again.
Decrease to negative infinity.
Yeah. Okay.
Then delete it.
So never invent a new operation, right? So make use of what has already been done. Reuse. Okay. All right. Change it to negative. There are two ways actually. One is change it to negative infinity, let it bubble up. Another way you could do it like heap sort we do. You take the thing, you sort, right? Okay. Right? But of course, after you don't want to just decrease it to negative infinity and leave the thing there, no. Because otherwise you have a heap where everything, the majority of the elements are all the negative infinity that you. It's like everybody sweeping the garbage under the rug, isn't it? Okay, let it be negative infinity, forget about it. Then your useful data is all hanging down below, and you will then have a hard time with finding minimum, right? Correct? So, okay.
We already paid the log n call.
When you always think like this, every time you make an operation, think about consequences, not the next step. After you have used it for 100,000 steps later, then you say, oh my God, every time I want to do something, I'm looking at all the negative infinity. So what you can do, if you bubble it up, it will reach here eventually. Okay? Another way, you can take this thing down and then bubble up. Okay? But you need to remove this and then do the union. Okay? All right. So, but it suffices to say you all agree with me can be done in order log n, right? Okay. So in that case, we have it. Everything can be done in log n. And it's very beautiful, right? Less than 25 minutes, I finished 20 minutes, I finished run everything. So this is very elegant structure. The structure is very beautiful. Okay, it has all kinds of nice property, and explaining it is also very simple. So this is a breakthrough. I think this is many people consider this to be a very beautiful data structure. We're going to see next why we don't often use this data structure so often. Okay, unfortunately. Okay. All right. The next part. Brings me to Fibonacci heap, and this part requires amortized analysis. Okay, most of you would have seen amortized analysis already, right? Anyone who have not seen it before, it's fine. If you haven't done, I think our 2040 covers it.
No, 2040 does not cover it.
Yeah,
I mean, I
I
covered it in my class. but not
analysis
officially.
algorithm would cover that.
Yes.
Okay, but never mind. So today I'm going to give you a reduced version of the amortized complexity. So you don't need to know the full-blown thing. Okay. Instead, I'll give you a fun take on amortized complexity. Okay. With permission from my former student.
Oh, was it the Facebook post? It is.
Okay. I'll give you instead amortized complexity in real life. Okay. All right. In real life, suppose I ask the question: how many of you keep your room clean and tidy all the time? That means I go there, so I do surprise visit and it is clean and tidy. I just pop into your dorm room and then it is clean and tidy. Okay, actually we all do amortize work, Okay, so suppose this is CTR. Okay, time to clean and tidy up the room. On the case day, Okay, day 1, day 2, day 3. The time taken to do that. Okay, all right. If every day you do a little bit, it is actually not so difficult, right? Okay, but we all know, okay? We all know, okay? CTR is too expensive to maintain every day. Every time I need to. So you see my office also, okay? Once in a while I go and clean it up when I cannot find my stuff anymore. Okay, but otherwise it gets messy, right? Okay? So most of us lazy most of the time, but once in a while, okay, we have. And this is what happened. On the 13th of September 2014, this is what, 5.5 years ago, this appeared on my Facebook wall. Okay, Su Yan was my student a long time ago. Okay, she's a graduate from School of Computing. I said, this is what happened. Me wake up, all blurry eye, chill in the bed, open the phone, see WhatsApp, message from mom. Oh, okay, open the message. Hi dear, are you home? I'm on my way to Singapore, arriving at 5 p.m. Okay, picture's face, make sure it's not dreaming, stare at the message, oh my God, this is real. And instantly transform into a high-speed cleaning robot. Okay, so that means that all this while, her CTR was very, very, very low. Didn't do anything. Suddenly must become a robot. Okay, so before you scream, you go and report to Jin Su Yan. You can see that. Okay, so she put all these things, and then I said, can be used for time amortized complexity. So I did ask for permission. I said, can I use your picture, to teach amortized complexity? Okay, so this is the next slide. I said, why? Okay, he said, can. This is amortized time complexity. Okay, so it's true, right? I think all students, you know what amortized complexity is. Okay, all right. She's still a good friend. Haven't thrown bad eggs at me yet. In fact, I just saw her recently at the Maker Fair. Okay, introduce some friends to her too. Okay, all right, Ken. So that is a quick round, okay, about what amortized complexity is. Okay, and I will do on what we call a need-to-know basis. Okay, I will talk about the amortized complexity. Okay, and I think the take-home message down here is this. Okay, elegance is good, but elegance may come back, okay, and cost you a lot more. Okay, so when we want it to be practical, okay, we need to be smart, lazy. Okay, be lazy but be smart about it. Okay, all right, in order to gain speed. Okay. All right. This, in case you want, this is good research article, also written by Bob Targent. Okay, this was a year later, 1985. Okay, all right. But this was the paper that talks about Fibonacci. Okay, fantastic. Okay, thing. Bob Targent is a very serious researcher. Okay, so in one paper he published a lot of results. Okay, so okay, this is the goal. Okay, if you recall, okay, where's my slide? I needed that slide back. That's why I haven't killed it yet. Okay, oh. If you recall, here's what happened. Okay, just now. Okay, E is larger than M, than V. Okay, E is the number of edges, V is the number of vertices, right? Okay, and so if in this case now both of them have the same complexity. In order to reduce the overall time, see, we started from this one being very big, V squared, to this one being E times log N. That one still, okay, N times, V times log V, sorry, V times log V, okay, and this is E times log V. So if you want to decrease some more, we need to bring this down. Actually, in my class, there's also another data structure between these two timing, before Fibonacci heap was invented. Okay, there was, if you look at heap sort, the heap going up, just now you will say when you shift up, take less time than going down, right, isn't it? Going up, you need only to check with the father, okay, or the parent pointer. Going down, you need to check which way should I go, left or right, right? Is that correct? So, if one way to improve it, okay, and decrease key, okay, only goes up, right? Decrease key, when you decrease the key, it only need to propagate upwards. So, in order to reduce the total time here, okay, I can afford to use more time over there, for example, okay? Then one simple way will be, how do I make the tree shorter? If I make the tree shorter, I will spend less time here, right? Is that correct? Okay. So, a very simple idea is this. I don't have to do binary trees, right? If I do a heap, I can do a ternary heap, okay? 4 heap, 5 heap, etc. Okay, and you can do that, okay? And it's all embedded in an array. You just change the mapping function. There is a mapping function that maps, okay, one position in the array to a 3 coordinate, right? All we need to do that. And so if you do that, then the height of the tree becomes smaller and we have fatter tree. Of course, going down is more expensive. Does that make sense? Now when I go down, I need to check against all the children to see. Now it's not just left or right, now it is one of the k children, right? So I can do this, I can increase this a bit, decrease this, and in that way make a balance and see where is the cut crossover point and do that. That idea was explored, okay, but I don't have the slides here, but you can guess what that will take you, okay? But the absolute one, this one, okay, Robert Targent aims for the absolute. I want this constant time, and I don't want to compromise this, okay? And in order to do that, okay, this was after binary heap was invented. I think it's a good time to take a 5 minutes break. Okay, I don't know whether, okay, or, okay. Do you need a 5 minute break?
Sure.
Okay, let's do a 5 minutes break. Okay, right.